All right. Good morning, everybody. Happy Wednesday. So I guess for today, I'm going to go ahead and just sort of continue off of last time's lecture. So last time we went into went over assignment one, but I sort of stopped at a certain point. So I went over the basic operations of this doubly linked list. So I'll just sort of cover a few more contents with it, and then of course we'll officially start actually CS302 content. Now, I was going to go over recursion a little bit, but I won't cover it just yet because assignment 2 that we're going to have is going to be a recursive program, so it's also a little 202 practice, if you will. So I'll definitely cover a recursion at that time. Just go ahead and just sort of continue from last time's lectures. So let me start the screen share right here, and we'll begin. All right. So we left off last time. We had this. I created this sort of linked list object and iterators. So in main, you have to create iterators in the following way. You have to say LL, the type, and then the scope resolution operator, iterator. Because remember, iterator is defined within the linked list class. So you have to, have this type of method to do this. And of course, if you want to have a null pointer or null iterator, just simply create an iterator object and just pass in null pointer into this constructor. So that way, end will be an iterator whose current is null. So you can use that to compare if you reach the end of the linked list when traversing your linked list using this IT iterator. And of course, tail insert and head insert, all of that. Just, tail insert inserts to the end, head insert inserts to the front. So technically, really doing this head insert, tail insert is not going to be too hard. It's actually very similar to a singly linked list because when you're doing a head insert, you're creating a node pointer, remember? So maybe I could just talk a little bit about this just to kind of help us out. But anyway, this is some code here I used last time. So remember, this is how you traversed the linked list using iterators from left to right. This was from right to left. Now, you could have made both of them into a for loop instead of a while. I just used a while and a for just to kind of show two different ways of traversing a linked list. But I could have, had this as a left to right traversal using a for loop instead. I just had these two separated just to show two different ways in case you're more comfortable with a while loop over a for loop example. So anyway, this was also from last time I went over basically that argv1 was sort of the because when you're going to run the program, you're going to use ./a.out and then have a command line argument to read in the file name into your program because CodeGrade for some reason does not really like CNing the file name for some reason. I don't know why. So we're going to use this method for testing on our end. So that way they'll be able to easily work on CodeGrade. So once you have this open, you end the file control loop, you read in one number at a time, and you just go ahead and insert it to the end of the linked list one by one, just like that. And then you're going to go ahead and begin this algorithm. So I'll go ahead and sort of, I guess I could talk about the insert. I guess I'll let you guys figure that out on your own because that's not so hard. I want to focus on the swap nodes function right now, and also give you an idea of how you want to actually implement the such and sort from main. So let's go ahead and, I see a question there. So the way I did it was you had a header file, and then what you do is you basically just have your class defined in your header file, and after you define your class, you implement the functions for your linked list class all in one header file. You just include that into your main file, and then when you compile, you just do g++ your main file because some reason templates have a hard time linking. So linking a header file to implementation to the main is kind of complicated with templates for some reason. So that's the reason why I'm having it all in one header file. So some students put everything into one, so they have their class definition and implementation all in their main file. That's okay as well. But I would suggest create a header file and then link that to your main file. Yep. And make sure the the name of your main file is assignment02.cpp. Otherwise, CodeGradle will not be able to compile. It's going to look for a file specifically called assignment02.cpp. But you'll find out when you're uploading it to CodeGradle, it will give you that error right away. So you'll know that, that happens. So you'll be aware of that. Yep. And then now I'm going to go ahead and just talk about the swap nodes function, and then go ahead and talk about how to implement selection sort, how to at least use all of this, and give you an idea here. So anyway, so for swap nodes, so let's say void. I think it's called a void ll type swap nodes. You're passing two iterator objects. Let's call this, I think I call it IT1. I'm going to call IT1. IT1, and then iterator IT2. I should probably have to do this in a separate line. I'm out of space here, so that's fine. So I'm not going to write the code. I'm going to go ahead and just kind of give you an idea for how to approach this. So I'm going to draw a linked list, just maybe not with actual values, just have a hypothetical linked list here so we can kind of see what's going on. So let's go ahead and create several nodes. So I'm just going to, try to draw, maybe try to do this a little nicer. So let me just see if I can use a box to make it a little bit easier, a little bit nicer. I think that might work. Okay. I'll go ahead and I'll copy it several times. Okay. So maybe I'll fall into some trouble there. I think it works. I think I'll be able to move these around. Perfect. Okay. So here is just a linked list of some sort. All right, and then I'm going to just, actually have to do it like this. I cut into thirds. So let's suppose we have the following linked list. So for the swap nodes function, we have a few different cases to handle. I'll just first draw this out. So each node number has 3 components. It has the middle box will be the data field, and the left and right boxes will be pointers that point to different nodes. So we can assume that maybe there's more nodes in this. We're going to focus on these nodes. So we have A, B, C, D, and E. So we're going to focus on just this part. It could be other nodes potentially. We're going to focus on this region over here in our linked list. So right now what could happen is the following scenario could happen. So let's suppose we have it where IT1, I'll have it maybe just point to, maybe for now have it point to, I'll have it point here. So I'll have IT1, it'll point to this node B, and IT2, I guess it'll point to D for right now, like that. So in this situation, you have a case where IT1 and IT2 are not adjacent to each other. So in this situation, we have to sort of create a few pointers. So what I would do is, since we're inside of the class LL, we don't really need to use iterators. That's mostly for main, to allow the user in main, or the programmer in main, to iterate through a linked list using a pointer, or using this iterator, which sort of emulates a pointer, if you will. So inside the actual function, in this function, we actually can create several pointers. So I'm going to go ahead and create a pointer. You can actually create pointers to say node star I1. You can set it equal to IT1 dot current. So create a pointer that will just point to that node. So for now, I'm going to go ahead and just rename this to be I1. So I1 will be a pointer, because I want to use pointers inside of this function because it makes it a bit simple. I don't have to use all this, current. I can just straight up use a pointer because it's a little bit simpler. And same idea, I'm going to create another pointer. Node star I2 equals IT2 dot current. So let me go ahead and just have a pointer I2 now. Okay, so I have to swap these two nodes in there from their geographic locations. So I want to have it where D is going to sort of be between A and C, and B is going to go between C and E. That's kind of the goal. So we don't just swap only the data points, we swap the entire node. You grab the actual node, lift it, and put it in between A and C, and likewise, same thing for B, between C and E. So if we have this situation where we have two pointers are now adjacent nodes, then we're going to create some extra pointers, which is what I did actually. So I'd say node star I1 left equals I1 arrow previous. So it's going to basically create another pointer, I1 left. I'll try to make it a little nicer. I1 left points to that. Then I'll create another pointer here. Call it node star I1 underscore right equals I1 next. So it's going to have this pointer I1 next point here. And of course, I'll leave the rest of this kind of open, but what you want to have is you want to create two more pointers. One that's going to be I2 next. And you want to have one that's going to be I2. Oops. Actually, I2, not next. I think I should call it right instead. I1 right. My mistake. I1 right. You want to have I2 right. And then I2 left. So you want to create four pointers. One that points to the node to the left of I1, one to the right of I1, and another pointer, one to the left of I2, one to the right of I2. As we can see, we have this situation right here. So now we have to do a lot of pointer reassignments because, so for example here, so A points at node B. Well, in order to swap B and D, A is going to have to point to D from now on. Let's go ahead and just make this happen. So how do we make it where this node points to the node D? So I1 left, arrow next. So I'm going to access the next pointer of this node and set this to point to D, which is going to be essentially I2. So remember what the arrow operator does. It's going to access that node. It's going to basically sort of take this node I1 left, access the next field, which will be this, and assign that to point to I2. Like that. And also, likewise, we want to have it so I2, sorry, points back to this. Because remember, if D is going to come right after A has to point to it, and then D has to point back to A as well. So I'm going to go ahead and say, well, I2 arrow previous equals I1 left. So to do that, I2 previous, it's going I2 arrow previous, so it's going to access this node, the previous field, and set it to I1 left. So I'm going to try to see if I can somehow put this here. This is kind of ugly, but there you go. And you have to do a lot more stuff. You also have to make sure for I1 next is going to be I2 right. Because you want to have it where if B is going to be where D was, B has to have it where it points to I2 right. I2 right points back to it, and so forth. And also to make sure that the I2 left next has to go to I1, and I1 has to go back. I1 previous has to go to I2 left, and so forth. So I won't do every single assignment, but you can see here it's going to be a lot of checks you have to do. A lot of pointer assignments to make this happen. Oh, um, I don't know if it's good or bad, but I've understood more about sorting linked lists in the past 10 minutes in the past. Well, I mean, that's good. I mean, right? I mean, that's a good thing because you don't want to be, if you understand it now, that's a good sign. I hope so. That's good. That's definitely good. Definitely better than not understanding it, or at least, so that's a good thing, I suppose. So I'll go with that's good. So that's that case. Now, you have to also be really careful about this as well. There's a lot more tricks in this situation. So here's one case. So what if I1 previous is null? So I'll put this here just to kind of help you. So I1 previous could be null. If that happens, that's fine. You have to check for this because if you try to do I1 arrow left, arrow, oh, sorry, I1 underscore left, arrow next, if you try to do this, it will segfault. If I1 underscore left, if that pointer is null. So I1 could be the leftmost node in the linked list. So you have to set I1 next to anything because there is nothing there. So you have to check to make sure that you're aware that's a null, otherwise it will segfault. Also make sure that I2 next could be null. That's also another thing to worry about. So make sure you handle that. Otherwise, if you try to do something like I2 arrow right, I2 underscore right, arrow previous, that's going to set it to, it's going to cause a segfault from happening. So make sure they don't dereference I1 arrow, I1 underscore left, or I2 underscore right, if those two nodes, or those two pointers, sorry, are null. So make sure you check for that. Also, what if, I guess this is also, let's say we have if head or tail point to I1 or I2. So if this is the case, if let's say you want to swap, let's say A and E. Let's say we only have 5 nodes in this linked list. You want to swap A and E. Then if you move A to the end, the head pointer will also move with A to the end. So you want to make sure you set A to point to the new head nodes. Let's say you swap A and E. Let's say A is the head node. Then what's going to happen is now E is going to be the head node. So head has to point to E from now on after you make that move. You sort of take A and E and move them accordingly, just like that. And same thing for the tail. Also, there's no guarantee that I1 is to the left of I2. So for this situation where they're not adjacent, it's not really a problem actually. So I actually tested it on my own, and the way I did it, it didn't cause any issues if I2 was the lefter node than I1. It still worked out just fine. But also we have another condition where what if I1 and I2 are in fact adjacent to each other? So I'll also write some more. So this is actually the case. This is basically if I1 and I2 are not adjacent. This case is really handled then. Now, you have to also handle a case. So what if I1 and I2 are adjacent? It's fairly similar code, except that just a little, you don't have to maintain so many pointers then. You don't have to maintain I1 underscore next, or I2 underscore previous doesn't have to be maintained in 2 variables because the left node is I1. So you don't have to really worry about that. But at the same time, also, I2 could be I don't know how to say this, the lefter node among I1 and I2. That's terrible grammar, but you have I1 and I2, but I2 could be that the lefter node. I think that, well, I guess not leftmost, because it could be just, I guess, leftmost among those two, I guess. So among the two, no, not the leftmost of the entire list, but the leftmost endpoint of those two nodes. I'll leave it as lefter for right now. We'll go, this is the kind of my first grade kind of grammar, This is the bestest, algorithm to sort a linked list. Actually, in fact, this method seems to be a little bit tedious, but it actually is the most efficient way to actually sort a linked list, because doing this amount of work, it's a lot of work here, but its runtime is constant, which we'll go over what that means when we go into actual algorithm analysis. But suppose if every single node contained like a vector in each sort of data field, then swapping data fields would take a lot longer to sort of, assign every element from one vector to the other like that. So this method of using this swapping mechanism like this is actually the most efficient way to sort two nodes. So if, let's say, the nodes contain integer data, you swap integer data, that's actually just as efficient as this. In terms of, in theory, theoretically, which theory and practice is kind of related somewhat, but theoretically, even practically, it's about the same runtime. Because you have, 10 lines of code or so, or 3 lines, is not going to make a big difference. But copying an array, if an array is very large, it's going to be much worse than just swapping two nodes like this. So we'll talk about constant runtimes and so forth later in the semester. But yeah, so to consider these cases. So also, if, let's say, if I1, I2 are adjacent, it could be where I1, I2 could be the head and tail. You have to also check for that as well. So it's really going to be, this function is going to be a nightmare to actually do. So I would suggest, either on some type of a writing pad or on paper, to draw everything out and write the code out on paper. So draw like the steps, like, just, okay, I'm going to set this pointer over here. Okay, so this is going to allow me to say I1 arrow next equals this. Okay, so I would say do it like that. Trust me. You don't want us to start coding this, because if you do that, you're going to fall into a big problem. So the scary part for me was when I drew this out, I spent like an hour really, drawing it out. Then I would leave the screen for a little bit, come back and relook at my drawing to see if it all made sense. Then I kept on looking at it. I was like, yeah, I'm pretty convinced this is okay. I compiled it and it ran on the first step, but I just was kind of scared because of what, that's supposed to cause all kinds of psych faults. But then afterwards, I ran some edge cases, and of course, then it didn't work. But for general case, it actually worked. So I was a little bit scared for a second. Yeah. Well, for the list itself, it could be duplicates in the list for the input, but I shouldn't really make a difference for this. So we can assume I1, I2 won't be the same node. If it is, I guess, if that's the case, that's a very simple check. If they're the same, just return. Just leave the function right away. But duplicates wouldn't cause a problem for this swap nodes. Yeah, and I guess, yeah, so in 218 to help, yeah, that's always good. Always first think before you start writing. Otherwise, spending hours debugging is definitely not fun. So it's always nice to first, get everything together first before you start, coding. So for this one, definitely I would suggest draw it out. It's not really hard. It's just that it's a lot of checks to go through to make sure it doesn't mess up. So that's the only hard part, really. But overall, though, the coding aspect is pretty simple. Just, all these stupid checks are a pain in the, they're a pain. So that's going to basically kind of, I'll give you a little summary right there on swap nodes. Hopefully that kind of makes sense in a way. And of course, at the very end, after you're done with all the swaps, after you finish all the work, you want to make sure that you want to sort of swap IT1 dot current with IT2 dot current. A simple pointer swap is okay, because when you move IT1 to a different location, IT1 current will follow that node and you position. You want to swap them because you want to have IT1, IT2 still point to that same. So if IT1 was pointing to that second node in the linked list, after you do that swap, you want IT1 to still point to that second node. Whatever that second node is different now, but it's still the second node of the linked list. So you want it to still point to that second node. So you want to swap them. So a simple pointer swap is good enough. You don't have to do any, just make sure you swap the addresses. So IT2, IT2, IT1 still point to that same position of the linked list, because in main is very useful. When you swap the two nodes, you want to make sure that those pointers still point to those same nodes, same located nodes in the linked list after doing that swap. So that's basically how you want to do this swap nodes function. No, you want to definitely swap IT1.current. If you modify I1, it modifies I1, I2 to move, but IT1.current will still point to that same node. You want it to point to that new node after. So you want to definitely swap IT1.current with IT2.current. Definitely want to do that. So let's go over how to use these pointers to sort of maybe try to emulate this selection sort algorithm. So what I'm going to do right now, let's go over the sort of the selection sort. So assume you have this list, LL int LST. Let's assume we have everything read in from the file and stored into this list LST. It's all there. So now we want to begin our sorting algorithm. So I'm going to create a few iterators. I'm going to have LL int. I'm going to call this maybe, I'm trying to use it for names here. I'm going to use just I. So I'm going to say iterator I, J, and I'll create this nil iterator, which I'll pass in null. So nil is going to be that null pointer. But remember, we're in main, so we can't use pointers to access the linked list directly. So have this nil iterator, and nil is going to be an iterator where its current will be assigned to null, because the constructor will pass in null into it, so it's going to assign nil's current to be that null pointer. Then I'll create another iterator. Iterator max pause for position. And then I'm going to say int max. Okay, so what I'll do right now is I'm going to create a for loop. So for I equals LST. So I'm actually going to do the following. I'm going to actually first, no, I think I'll do it like this. So I'm going to say J equals, I'm going to assign this for right now. Let me see, how do I do this correctly? So I'm going to set it equal to nil for right now. Yeah, I'm going to do that. Then I'll say for, I'll say for I equals LST dot begin. And then while I not equal to J, and then J minus minus. Now, this would segfault, but we're going to set J, we're going to set it to a new node after. Because the first step, you have to go through the entire linked list to find the max. Next time around, you have to go through everything but J. So this is going to kind of help us out with this. So we're going to set the max equal to star I. Remember how the max works. We first assume the first element is our max element. And then, of course, I plus plus. Yes, so we're going to update this in a second. So what we're doing is we're going to have I always start from the front, and every time J is going to go down one level. So we'll see in a second how this is going to work. So this is how I did this. So now we're going to have another loop over here. So I'm going to say while I not equal to j, we're going to say, so if, actually I have to do one more thing I have to do over here, my mistake. I'll put this right here. We want to set the max position equal to I. So I think I'll put this right over here. So if max is less than star I, what is the word after j equals? Equals nil, which is going to be this nil pointer. So we're setting j to null right now, initially. Yeah. Oh. Yeah, so it's supposed to be a semicolon. You can decrement nil, but we're going to set j to something else before the outer loop does one iteration. Just that way it'll be able to correctly decrement. So here, I'm going to go ahead and just, so we have a case where if let's say this I is larger, then I'll leave this part blank, but you want to update your max, and also you want this max position to always point to the node who has the biggest value, and increase I by 1 afterwards. This will allow us to traverse through the entire list. So once I equals j, then we're officially done at that point. So now we found the max element in our list. So, we have, at this point now, we're going to do the following. We're going to say, well, if j equals nil, I'm going to set j equal to lst dot end. So now j is going to point to that rightmost node of my linked list. So I have to basically swap max position with j. J is my rightmost element. So I have to take the max element I found and swap that with whatever is in j. And that's about it, I believe. And now, go to the very top of our loop, j decrements by 1, and we can look at I and j. So now what happens is that we sort of, actually, I'm trying to think, this might be a little bit flawed because we want to look at the last element as well. So let me see here. I don't want to give too much away, but I think this is actually on the right track. But I think one issue is that this is not going to work completely because we want to actually, when it reaches j, because in this situation right here, if j is the very end element, then what's going to happen is that when you do this while loop over here, once I is equal to j, it will stop looping. But the last element where j is could be where the max element is in the list. So you want to maybe do one more check afterwards, potentially. So I'll just kind of leave this open for right now. I'll write some notes here later on, but this is the general idea, though, for sure. Now, you can also, on your own, devise your own method of doing this as well if this doesn't make sense. But the idea is that what I'm doing is inner loop portion will traverse the whole list. Once it hits j, it will stop. It will find that max, swap it with j, and then j decrements by 1 to the right. So it keeps getting closer and closer to I. So eventually, in this for loop, once j does equal I, then the whole list has been sorted. So what we do is we go from I all the way to j, then we go from I to j, but j gets closer and closer to I. So it's going to loop to every element except for the last elements that have already been found as the max in the previous steps, if that makes any sense at all. So I think the only issue I have here, which I kind of don't remember how it is exactly, but you want to make sure that, because in this case, j could contain the max element, because this situation now, j decrements by 1 in this situation. So I also could write some code here to make sure that it does actually go to j specifically, because this case, j is actually going to be the element to the left of that max. So that element to the left could be the max of the current list potentially. So, but this is sort of the idea. So no, you're gonna first just populate the list and then perform this sorting algorithm. So yeah, otherwise it becomes, I guess you could still do it, but this way, I guess it's sort of just a little more efficient. If you do this every single time we have to insert, it'll be a slower runtime. This will definitely make runtime a little faster if you do it like this instead. So that's the idea. So I have these endpoints I and j that tell me what part of the list I'm trying to find a max element in. And then when I do, I swap it to the j position, move j closer to I, so that tells me the two endpoints of the list I'm trying to find a max element in. Because everything after j is already in a sorted position. But from I to j, it's still an unsorted list. So j keeps moving closer to I as we do this. Whereas inner loop just finds the max within I and j. Then we swap it to j gets closer to I. So I think this has to do maybe one more step, because once I equals j, you have to also check one more time, because there's a case where at index j is where the max could be potentially. So you have to also do one more check over here. So I'll put this maybe here in note form, that j could contain the max element if it's not a nil iterator. That's about it, I think. I think that kind of goes over it. So I guess, since we didn't really cover such in sorting class, this is kind of my way of sort of, covering it. But really, it's a very simple algorithm. It just, the hard part is on this linked list structure makes it a bit more challenging. And of course, that swap nodes and everything. So yeah. So for right now, it's due on Monday. But I guess, we'll see. We'll see how things go, and we'll see if it's still going to be due Monday or not. We'll find out later. But for now, it's due Monday. We'll just say that. Just for now. Temporarily, it's due on Monday. Or I guess, I could just say, well, if nobody has any questions, then I guess, we all got it done, so we can have it due on Monday. Or I could maybe assume that means, maybe people are very busy working on it, so maybe that's the case. I don't know. But we'll find out. So anyway, any questions on this at all? Not yet. That's a good answer. Not yet. Alrighty, so let's see here. We got about another half hour or so left. So, okay, let's go ahead and now. So I'm going to go over the recursion sort of content next week when I give out the new assignment. So I won't cover recursion just yet. I want to have to bounce. I don't want to really throw too much at us at one time. So I'll cover recursion when we cover our new assignment next week, which will also be sort of a review of CS202 somewhat. So, I mean, a do while would be just as fine. So it's really, you don't have to use a for loop just because, but it's really, there's no rule in doing it like that. Maybe I used a while loop in my version as well, but I can't remember what I did exactly. I know it was something like this. I just can't remember the exact code I wrote, but it's up to you. So I'm just giving you a little bit of advice, but of course you can have your own implementation of this algorithm. So basically, I kind of gave you this code sort of. So let's say if your code is very similar with Moss, I'm not going to really come at you because very likely you may have a lot of similar code here. But for swap node, I kind of gave a little bit of help, but it would be impossible to have swap node. Maybe this part might be the same for everybody, but then what you do over here though is going to be very different. It's unlikely to be exactly the same. So that part's the only spot where I can definitely tell there was copying going on. Everything else in this program is kind of, at least for like, insert to the front, there's really not many ways you can really do that. And I gave you the main code here kind of for selection sort. So there might be some similarities, that's fine, but swap nodes are I'll be checking mostly for similarities because I didn't really, give you exact code. I gave you an idea, but not like, exactly follow my code, line by line, just only the first few parts and that's it. But much more lines of code you have to write for swap nodes for sure, because there's a lot of stuff you have to check for. So anyway, I'll post these notes up on Canvas, and I'll now begin talking about actual algorithms. Oh, so for swap node, basically, the two main cases is if I1, I2 are not adjacent and I1, I2 are adjacent. And then also, for either case, for either adjacent or not, I1 previous and I2 next could be null. So if you try to do I1 underscore left arrow next, it will segfault. So make sure, do this line of code right here only if I1 arrow left is not equal to null. And same thing for I2 arrow, I2 underscore next, same thing. Because what if we set I2, as we have like I2 underscore right, this could be null potentially, because this node I2 could be the last node in the linked list. So if you try to do I2 underscore right arrow previous, it'll segfault. So only do that only if I2 underscore right is not equal to null, then try to make that move happen. Also, make sure that head or tail could point to I1 or I2. So when you do that swap, when you move I1, I2, you swap those nodes, make sure you also swap the addresses of head with I1 and tail with I2, or vice versa, because I1, I2, I2 could be the left of the two. So I2 could be further left than I1. It's not going to always be guaranteed. Now, when you run your code in main, maybe you're going to handle that case, but there's no guarantee. Maybe somebody who uses this function, let's say, could have it where I1 is the more right node than I2. So I could actually put some extra tests in there in CodeGrade to check for that as well, but I'll probably just not do that just to not make this terrible. But if it works for the section, so you're fine, but just be mindful of that. So these are the cases kind of listed out over there. Yeah. Alrighty. So now let's go ahead and officially discuss algorithms, I guess. That's sort of, what this class is kind of about. So let's go ahead and now talk about algorithms for the first time. Kind of intro to CS302. So let's ask ourselves, what's a good question to ask? Well, what is an algorithm? I kind of sound like a philosopher. What is an algorithm? Why? Where? When? And how? I don't know. It's philosopher talking. Yeah, so the answer right there, a set of steps to achieve a goal, is that the right definition? That is what an algorithm actually is. Let's go ahead and write this out. So I'm going to go ahead and just say it's a step-by-step process to solve a problem. Now, step-by-step really implies that most algorithms are going to be deterministic, so it can't just guess. It has to kind of do everything step by step. So that makes sense. Now, another thing, I want to add to this is that for all input, the correct output is always obtained. Which makes sense, because for an algorithm to be correct, it has to always work. So think of section story you're going to be working on for assignment 1. If for certain input doesn't work, then it's not really a correct algorithm. I mean, maybe it's close, but in order for it to be truly correct, it has to always work for any situation, which makes sense. So think of any sort of algorithm, for example. If it works only for certain instances, well, then it's not really valid. It's just, okay, I mean, it is what it is, but it's not really, it doesn't really solve the problem, which was to sort this list. So that's another thing. Also, this last bullet here will be for must finish in finite time. This is definitely one of the topics discussed in computational theory, with automata theory, is, it must finish at some point. So, for example, here's one way to try to be cute for assignment 1, but it won't work, is that have your program just have infinite loop in there. And then the question is, well, does your program work? Well, we can't really tell, because the only way we can tell is it has to output the list. Then we can compare if that list is, correct or incorrect. So that's how we know it works. If it's running forever, there's no way we can mechanically prove that it's going to eventually stop with an output. Now, of course, for code grade in assignment 1, if it runs for a minute or two, then okay, something's wrong with this program at that point. But theoretically, though, there's no way of guaranteeing it will stop. So you can't say that it's not correct because it didn't stop and give you the output. You can't say it's correct either, but you can't say it's not correct. So all you can say is that, well, it's open, it's still running, so we don't know if it's correct. So that's one of the big sort of definitions in computational theory is undecidability. So it has to eventually stop, essentially. Otherwise, you can't tell it's correct. Well, I mean, I guess they don't. I guess they keep running forever, but they're constantly outputting something, so it is progressing at some. Yeah, I guess for video game algorithms, I guess they're constantly running because input's being constantly fed in. There's always something is always changing, I guess, and has to keep on running for every new event. Whether you move or as the time progresses, things are happening. So that's probably just keeps running over and over again. So it's not really infinite looping in a way. Just things are keep happening. So then it has to keep on, has to keep on doing that. So that's a good question. Yeah, because something's always happening, I guess. So it's not really, I guess if the game just froze, that would be the equivalent of infinite, then it just froze. That's it, we're done. But if it's constantly moving, then it's just getting more inputs. So we'll just say it like that. So the next sort of, oops. Okay. So the next topic with algorithms is that, well, how do we measure its efficiency? So how do we measure the efficiency of an algorithm? Now, we could think about space, like how much memory it takes up, but I'm not a big expert on space complexity, and usually I think space is not a big problem, but time is always the issue. So time. So we want to have a fast algorithm to solve some problem. So, okay, so we basically use time as our factor. So if it takes less time, then it's more efficient. It's a better algorithm compared to what takes more time, which I guess makes sense. So how do we measure time? So I guess I'll put another bullet here. How do we measure time? Yes, we're definitely getting philosophical here now, aren't we? Because how do we measure time? Well, how do we measure time? Well, what's time? So, okay, so here's one idea. Okay, so we could think of it as we have sort of, we have a program running and we just sort of clock it to see how fast it takes. So that's one way you can sort of measure time. So we can use real time, which is going to be, minutes, seconds, hours, days, and etc. Now, that method is okay. There's one sort of problem with it. it depends on what machine you run your code on. So for example, if you take, a program, let's say selection sort that you're going to write. You take that program and you run it on old Apple II from 1984 or something. It's actually before my time. I wasn't born then, I don't think. So, wow, that's gotta be old then, 'cause I'm the old guy here, so that's gotta be old. So, the thing is, on those older computers, it had a slower processor. Didn't even have a GPU, I don't think, even. So it was definitely all right. That's good to hear. So, so basically, um, having an older hardware, it ran the code slower inherently. So your same algorithm that you wrote for selection sort, you run this on a newer computer with nice, i9 processor and the 3090 graphics card and all that fancy stuff you have. And it runs that code way faster, much less time. Then the question is, okay, is that code better because it ran a faster computer? And the idea is no, I took the same exact code from Apple II, ran that on a newer machine and ran faster. Well, it's like, yeah, of course it ran faster, faster machine. So the problem is that there's all kinds of computers that exist today. So some are faster, some are slower. So real time is not the best benchmark. Although we could use real time, but really a better approach is going to be um, the amount of steps needed to complete the algorithm. So otherwise known as the growth rate. So number of steps it takes to run a selection sort is sort of the runtime. And that number of steps is the same number of steps as if you used a newer computer or an older computer. So the steps is what really matters. And of course, if you know how many steps it takes, we can compute the amount of time it would take on computer A or machine B. Let's say this machine can do a billion instructions per second, then you can sort of compute and scale how many minutes it would take because this algorithm it runs this many steps and so forth. So number of steps, you can translate that into actual real time, but number of steps, it's more universal because it doesn't matter what computer you're using, it's going to be the same no matter what you do. So selection sort, the amount of steps it will take will be the same on my computer, your computer, any computer. It's the same number of steps it will take. But the amount of steps, maybe for some machine, each step takes less time than different machines. That's why it might be faster on certain computers. But the idea is that we want to look at the number of steps it takes. So basically now we have to sort of define a few different ways of categorizing algorithms into its runtime. So we have a few of these. We have one thing called big O notation. Big O notation. Let's define that. So we have f of n equals O of g of n. Okay, so f of n is going to be an algorithm, and n, so for any input, n is always going, so any program, n is going to be always the input size. So given the input n, f of n is going to tell us how many steps this will take with respect to n being the input essentially. So f of n is going to be our step amount. So basically all of these algorithms will have some type of a function. So for example, like n over 2 could be a function. So as n gets larger, the runtime number of steps increases n over 2. So if input is 100, it'll take 50 steps. If input 200, it'll take 100 steps, and so forth. So this function sort of maps the amount of steps it will take given some input n. We'll do a lot more examples of that later. It's starting to annoy me now. Okay. Better. So now we have the following. So let's go ahead and define. So if f of n is in a set O of g of n, let's take a look. So the equal sign here is really not equals. It's really more of a element or belongs. So f of n belongs in O of g of n. We'll define that in a bit here. So definition is f of n, if f of n is equal to O of g of n, that means the following has to be true. Where c is some constant bigger than 0, and then n is bigger than some starting point, n naught, I guess they call it. So if you pick some starting n value, and n just goes to infinity, you pick some constant c, if this works, f of n belongs to O of g of n. So let's go ahead and do a few examples, and we can nicely, more formally define, kind of in more layman's terms, what does this all really mean. So let's go ahead and do the following. Let's try n equals O of n. I'll leave definition here for a second. So is this true or false? Well, one way to find out, right? Let's go ahead and test it out. So I'm going to go ahead and say, well, okay, n less than or equal to c times n. Okay, well, if let's say c equals 1, and n naught equals 1, then this inequality will always work. Therefore, that's a thumbs up. That's definitely in the set. So n is in O of n. Guess that wasn't too shocking. Okay, how about 50n equals O of n? Let's test it out. Let's see if it actually works. So we're going to have 50n less than or equal to c times n. So pick any constant, pick any starting point. I'm going to make this simple again. I'm going to choose c to be just 50, sure. And n naught will just be 1. So n naughts are starting n value. So from 1, we're going to run to infinity. And c is going to be some constant. We pick just a constant. That doesn't mean every constant, just pick one constant. So if I plug in 50 in for c, and my starting n value is 1, this inequality always works. So I guess that also worked as well. Let's do some more examples. Let's try n over, I guess maybe I'll try, let's say something like 3000 n plus 5000 equals O of n. Well, let's see if it works. This is actually pretty large, so this might not really work anymore because this is much bigger than these two functions right there I use. So I don't know, but let's go ahead and figure this out. Let's see. Maybe it'll work still. I don't know. So 30,000 n looks like plus 5,000 less than or equal to c times n. I'll put this to the side here. I'm going to say n naught. I'll make it 1 again. And c, I'm going to choose 35,000 for some reason. And now I'm going to have 30,000 n plus 5,000 less than or equal to 35,000. Oops, that's too many zeros. N. Yes, I'll show in a second why it shows that. It could have been anything, but it shows that just because. So I'm going to go ahead and split this up. So 30,000 n plus 5,000 less than or equal to 30,000 n plus 5,000 n. These two cancel out. As long as n is 1 or larger, this inequality has to be true. That's why I chose that. I could have chosen 40,000, that would have worked the same way. So basically you pick just a constant of any kind. It doesn't matter which one, just pick a constant. And then pick a starting n value where n will start from 1 and go for infinity, I suppose. And if inequality always holds, it has to be in that set. So basically, I could also try another function as well. I'll just do one more. This would be a little bit of an easier one. So I'm going to go ahead and just move it down a little bit. So let's try like n over 10 equals O of n. Let's see, n over 10 is definitely smaller than other ones, so maybe it's not going to work anymore. Let's go ahead and figure this out. So we're going to have n over 10 less than equal to c times n. And I'll just pick, okay, n naught will just be 1. I'll pick c equals 1 in this case. Any constant will do, actually. So n over 10 less than equal to n. Well, as long as n is 1 or larger, which it is, this always holds. So the conclusion we can make out of this is that O of n is a set of linear functions. So for O notation, we don't typically ever say this. So I'll write this right now, and I'll erase it in a second. We don't say O of 10n. We don't say O of 5000n. We just say O of n, because 10n, 5000n, any function that's linear, all is in the set O of n. So O of n is an infinite set of linear functions. So any linear function, any linear growth rate is going to be in O of n. So O of n is an asymptotic complexity class. So I'm going to go ahead and just put this here. So O of n is an asymptotic complexity class. It's basically a class of linear functions, or a set of linear functions, whatever you want to call it. But it's a set or a class of, so it has all linear functions. So asymptotically means that they're all growing at the same rate, at that linear rate. So any function you think of as linear all has that same linear growth rate. They're all kind of classified into this set O of n. There's actually many different asymptotic complexity classes, but O of n is one of them. But there are more of them as well, which we'll talk a few more. We'll talk about other ones as well. But let's go ahead and also test out the following. So this, let's say we have n squared. Is it equal to O of n? Now I just said O of n is a set of linear functions, so it should be no. But let's go ahead and just try to think about this let's try to convince ourselves that this is actually not true. Let's go ahead and do the following. You know what? I'm going to go ahead and just be, very daring and say the following. Okay, I'm going to say n squared less than equal to c times n. Okay, I got this. I'll be able to knock this n squared out, no problem. I'm going to pick c to be a really big constant. Yeah, this is definitely going to work. A very big constant. And n naught, I'll make this a very large constant. Actually, I'll make it just 1 because otherwise it'll mess up. So I'm going to pick a huge constant for c. A really big constant I'm going to pick. So, yes, for the very beginning of this, if you graph these two functions out, at the beginning, of course, this huge number in front of n is going to be bigger than n squared. Yeah, that makes sense. But eventually, as n gets larger and larger, sooner or later, this n squared sort of growth rate will pass this linear growth rate. It doesn't matter how big c is, because the problem is that c is a constant. C is fixed, and then n is not fixed, n is growing. So n squared has a very big growth rate, much bigger than n. So what's going to happen is sooner or later, n squared will pass any linear function. Let's take a look. Well, I mean, mathematical one's required maybe for some of the calculus stuff I might do later in this session, this semester, sorry. But yeah, a little bit early on, calculus will be important early on in this semester. But yeah, it's kind of, I guess, why calculus might be important for this. So, but the idea is that the growth rate is off by a factor. So n squared and n is off by more than a factor of some constants by a factor of n. So as n gets larger, that growth rate factor also gets larger. So that's the problem. So a constant off is actually not a problem. Yeah, eventually it will reach C, that factor will reach C, and then it'll also pass C, and then that's it. So therefore, this can't be correct. So it's not going to work actually. So that means O of n cannot really, so n squared, any quadratic function, no matter what I pick, n squared over a billion, even that is not in the set O of n, because same idea, has a quadratic growth rate, it will eventually pass any linear function if n becomes large enough, which n is going from 1 to a very big amount. So n can be any size basically, and so for that reason, we can't bound this. So O of n only contains the linear functions. However, let's try another example here. Let's try root of n equals O of n. Is this correct? Is this a valid statement? Well, one way to find out. Let's go ahead and just use math to prove this instead of having to just believe me, or let's try to prove it mechanically, so we don't have to just believe, we know. So in this case, I'll pick C as 1 and not as 1. So I'll substitute those in. So we have root of n equals n. Sorry, less than equal to n. And then I'll say, well, I can just sort of do the following. So 1 less than equal to root of n. So this is going to be always correct. Even if n is 1, I believe it's also correct. So yeah, so basically this is also true. However, this statement is not a very good statement to make. Because yes, technically, by definition, yes, this is true. So to expand our definition of O of n contains all linear growth rate functions and also lower than linear growth rates. In this case, root of n is asymptotically smaller than n, but it's also in the set O of n. O of n is the upper bound. So anything that has linear or less is in this set. Anything above linear, however, cannot be in this set. So this question is valid, this statement, but it's almost like asking a question, are you shorter than 1 mile? And, well, yeah, I think. I can't imagine. I mean, even in that goldfish commercial, what's it, Boban? Boban bag, he's a pretty tall guy, but he's not taller than 1 mile. I mean, although it might seem like he is, but he's not. So the thing is that this is correct technically, but it doesn't tell us anything. So you want to typically lower the upper bound. So O of n is your upper bound. You're setting the bar kind of high. You want to set that high bar, as low as possible, but still contain this set, or contain this function, I'm sorry. So this is actually a correct statement, but a stronger statement would be to say, I'll use this pen instead, root of n equals O of root n is a better statement to say, because that's actually much more closer, because this way that bar is set right on top of it, so it's not way off. Otherwise, if you put it way up, like I could also say that, I could say this as well, but that's a bad statement to make. So root n has its own sort of asymptotic class, if you will. So you want to always try to lower the function in O of n, or inside the big O, just to make sure you have a nice, more stronger statement, because otherwise it doesn't really tell you which one is better or worse. Because, okay, fine, I can say every algorithm is exponential runtime. Okay, fine, but we want to know which one is really better. So doing that is really, you want to always try to have the upper bound lowered, so we have a better idea which one is better or worse. So we'll see later on, but that's kind of what you want to do. Let's see here. Yes, so in the previous example, if I were to say n squared equals O of n squared, absolutely we can say it's correct. We can easily show that using our definition of big O. We'll have the following. I'll just put this here for a second. N squared less than equal to c times n squared. Pick a c and an n naught value, and you can definitely show this inequality will always hold for any n. So pick a c value that's going to work, of course. So basically, you pick some starting n value, n keeps on growing, and you pick some c value, some fixed constant, and then you have to convince yourself that this inequality always holds for every n beyond n naught. I'm not sure. So why we use this this sign instead of the like the element sign like that? I think that's how it looks like. I think because this big O notation was actually created before set theory existed, I think, and that's the reason why it's like that. So the equal sign really means set notation or belongs or elements. So it really means belongs in the set, but it might be because of that. That's all I can think of. That's the only reasonable explanation as to why equal sign is used instead. Yeah. So I guess we're almost done with class. You have 3 minutes left here, so I'm going to stop right now. We'll continue this more next time. Of course, I'll have a new assignment up next week some point. I'll cover that as well. And after I finish the assignment review, assignment 2, I'll talk some more on this. So take care, you guys. Have an awesome weekend. Stay safe. Thanks for watching, and I'll see you guys next week.